Okay, continuing on our sensitivity journey, we just talked about what happens if you add a new variable. Well, next up, we got to talk about what happens if you add a new constraint. So adding a new constraint will make the feasible region smaller or potentially leave it alone. If the constraint is sort of away from the feasibility region, it might not really affect anything. It will not affect optimality. That is, if the previous optimal solution is still feasible, then it will still be optimal. Okay, and so what we need to do, last time we checked a dual constraint, this time we'll need to actually check the new primal constraint. So let's think of a scenario where that might happen. Well, Geppetto realizes that he's got a limited supply of wood to make the toys this week. Story we hear all the time, there's supply chain disruptions going on, so he needs to refactor what's his plan for making soldiers and trains this week. We'll keep it at just the soldiers and trains problem. Forget about the stacking towers and the wood blocks. Okay, so he only has 50 board feet of wood. A soldier takes toy soldiers take 1 board foot. Toy trains take 2 board feet. Is his previous optimal solution, which was 2060, still feasible? Well, let's look at that new constraint. That new constraint would be 1 board foot per soldier. So 1 times x1 would be the number of board feet used up by the soldiers, plus 2 board feet times x2 is the number of board feet of wood used up by the trains. And we'd want that to be less than or equal to the available supply of wood, which is 50. Okay, plugging in his current solution, that's going to be 20 plus 2 times 60 equals, let's see, 120, 140. Okay, his current optimal solution uses 100 board feet of wood, and that is definitely not less than or equal to 50. And so our current solution is not feasible. Not primal feasible. Maybe we should be a little bit specific there. And so it's not primal feasible, means that we can't keep making 20 soldiers and 60 trains to get that optimal profit that we had before, because we don't have enough board feet to do that. Okay, so let's go ahead and add the new constraint into our Tableau. Okay, so I'll go ahead and copy it down. I'll pause the video. You copy. Okay, I've copied down the old Tableau. But what you'll notice is I add an extra column here, slack for wood. We added a new constraint dealing with the amount of wood available. And so I added a new slack variable that I'll need for that constraint. Here, let me label the rows. And so this is x1, x2, and slack for demand are my current basic variables. A new constraint corresponds to a new row. And so let's introduce a new row. This row, we'll use the slack variable for this new constraint as the basic variable in that row. And so let's kind of copy this down to here. We get a 1, a 2. None of the other slack variables show up in this constraint. We'll add a slack for wood variable here to change our less than or equal to into an equality. And so we'll get 1 there, and then a right-hand side of 50. The slack for wood doesn't show up in any of the other constraints, and so we'll put in zeros there for all the other constraints, as well as the objective value. The slack for wood variable doesn't show up there either. Okay. So here we go. There's our new row. The thing to notice here is that we're not quite in what we'd say is kind of standard format, or not. We don't have our standard basis vectors showing up for all of our basic variables. We've kind of got the right standard basis vector here and here. That's fine. But over here, we'll want this to be a 0 and this to be a 0 for x1 and 2 to have their standard basis vectors. So what we're going to do is we're going to do row operations in order to zero out this and zero out that. And so I'll go ahead and, yeah, so let's see, we're going to want to take -1 times this row and add it down to here. And we're going to want to take -2 times this row and add it down to there. And then we'll use that to then replace this row. So I'll do it in a new color. It's going to be an updated version of that row. We're going to have a 0 here. The goal is to zero this out. So -1 plus 1 is going to be 0. -2 plus 2 is going to be 0. I'm going to do both these operations at the same time. So I'm going to take -1 times this plus -2 times this plus this row here. Okay. So -1 times 1 plus -2 times -1. So -1 plus 2 plus 0 is going to give us +2 there. -1 times 1 is +1. -2 times 2 is -4. So 1 minus 4 is -3. I'm going to get -1 times 0. -2 times 0 plus 0 is 0. And that's what we want there. And zeros plus our 1 is going to keep us at 1. -1 times 20 plus -2 times 60 is going to be -140, plus the 50 is going to give us -90. Okay, notice that the kind of value of -140 matches up with this 140 here. And so we're essentially taking the 50 on the right-hand side and subtracting this over to there to get us our new right-hand side of -90. Okay, I'll go ahead and cross this row out because that's what we just replaced there. And this is our new bottom row. But you'll notice we've violated one of the sort of fundamental rules of the simplex method, and we now have a negative number on the right-hand side there. So what can we do about a negative number there? In all the kind of simplex practice we've done so far, we've sort of always had positive numbers on the right-hand side, and we said that having a negative number on the right-hand side is sort of an indication that we made a mistake and we've moved into the infeasible region. And the whole idea of the simplex method is that we're moving from basic feasible solution to basic feasible solution. And so all of the steps, we should always be in the feasible region, or at least on the edge of it. And we could maybe think about some way of introducing a big M method to this, but actually we don't even need to go there if we're willing to use what's called the dual simplex method. The best way to think about the dual simplex method is to think of it sort of as the simplex method backwards or sideways, or kind of backwards and sideways maybe. So here are the steps. A dual simplex method should start with a dual feasible solution, which means that all the objective row values are non-negative. Kind of looking at what we had here, yep, they're all non-negative. Okay, so you should start with all those staying non-negative. So first thing is we check for feasibility. If the B column has no negatives, then we're both dual and primal feasible, which means we're done. Okay, so remember, if we have kind of our complementary solutions and we're both dual and primal feasible, then we're actually optimal. Okay, and that's the real power of complementary solutions. So our order here then for selecting exiting row and entering row is reversed. We select our exiting row by choosing one of the rows with a negative in the B column, or that right-hand side column. And so in this case, we'll choose this column as our exiting basic variable. Now for our entering basic variable, we do a ratio test, but sort of a different ratio test. So we want to divide the entries of the objective row that have negatives in it. Okay, so we want to check that exiting row for negatives. Looking along here, there's actually only one negative right here. Okay, then we want to take values in the objective row, divide them by the negative entries. And so 1 divided by -3 would be -1/3. And we'd choose the smallest in absolute value of those. Okay. In this case, there's really only one negative in this exiting row. And so we have to choose that as our entering column. Okay, but if you were to have more than one negatives, you take objective value divided by any of the negatives, corresponding negatives, and you choose the one with the smallest absolute value. Okay, they'll all be negatives because we're specifically choosing the negatives there, but you'll choose the one closest to 0. Okay, and then you go ahead and pivot on that combination of row and column, and you repeat steps 2 through 5 until you reach primal feasibility, which would be dual optimality. Okay. I've got an extra page on the next page. I'll go ahead and copy this down and show you the pivot step and what we get to after we do this pivot here. Okay, so we'll pivot on this row. Notice now we're going to try to get a 1 here, and so we'll divide this row through by -3, which will make this number positive. Okay, we're trying to really get rid of the negatives on our right-hand side. So I'm going to pause, copy this down on the next page. Okay, as I was doing this next step, I realized I made a slight mistake. That should be a 1 there in this when we sort of take -1 times this row and -2 times that row and add them to the 0. We should just get 1 there. Okay, so I changed that over here. So here's our tableau as we copied it down. Here's our exiting row, our entering variable, our entering column. And so we're going to divide this row through by -3, and then go ahead and try to eliminate each of these values here and turn them all to 0s. And then once we do that, we'll end up with this tableau. And what you'll notice, or I'll kind of point out a couple things here, is that our optimal solution or our objective value decreased. Okay, so yeah, that's something to notice is the objective value went down. Okay, because we're now constrained on this extra resource. We can't make as good of decisions as we would have if we weren't limited on this resource. And so we've essentially caused a reduction in our optimal solution or in our objective value. Okay, here's the new tableau after we do that pivot. We'll notice that we are not primal feasible, which means that we're not dual optimal, which means we got more steps to do. But we'll notice that if we look up here and we're checking this for negatives, we're sort of still dual feasible, which means we're sort of optimal in the original problem, but maybe super optimal is the way to think of it, is that we're optimal, but we're sort of outside the feasible region. We're better than the optimal solution, but we violated a constraint to get there. Okay, because these are all positive, we're dual feasible. Okay, and so let's do another step because we're not primal feasible yet. So we look through and we see this -10 here. That's what's causing us to be not primal feasible. And maybe I should maybe make a note here. What's our current solution here? The current solution is that x1, maybe back this step, x1 equals 20, x2 equals 60. And we've got some extra slack in the demand constraint of 20, and then the slack for wood is -90, meaning that we're violating the constraint for our wood. And now after one step, x1 is now 50, so we're making more soldiers. We've reduced the amount of trains x2 down to 0. SD is now -10. So we're now making too many trains that we're violating the demand constraint for trains. And SC, which is the slack for carpentry, is now 30. So now we've got extra carpentry labor on our hands because we're making fewer trains. And so now we got some extra labor for us to use. But we've got the negative here, so we're going to choose this as our exiting row. And if there were multiple rows with negatives on the right-hand side, we could really choose any of them. Okay. Now we go ahead and scan across here for negatives in this row, and there's only one negative, and it's right here. If there were multiple negatives, we'd do the ratio test of the corresponding objective value, which is 2/3 divided by -2/3, which would be -1, and we choose the closest to 0, okay, or smallest in absolute value. But since there's only one negative, this column wins out as the entering variable. And so slack for finishing is going to enter the basis next. And so we'll gain some slack for the finishing constraint. Go ahead, pause the video, do that pivot, and we'll see where we get to after that pivot. Okay, here's the tableau after that pivot. So here we got, we'll notice now that we look at our right-hand side, all of these are positive. And so at this point, this is primal feasible, which means that it's dual optimal. Okay, and that's sort of what the dual simplex method is working towards. Notice looking up here, we're still dual feasible. Okay, and again, if we look at our objective value, is that the objective value decreased again. So from 180 to 150 to 140, that objective value is going down with each step. We're working from being sort of super optimal and outside the feasible region, trying to get back towards the original feasible region. And to do that, we've got to give up something in our objective value. Okay, the new optimal solution, we have X1. So since we're since we're primal feasible and primal optimal, this is our new optimal solution. We don't have to do any more steps of the dual simplex method. Our new optimal solution is X1 equals 40, X2 equals 5. We've got slack for finishing of 15 hours, and we've got slack for carpentry of 35 hours. And so we're sort of underutilizing our labor, and that's sort of a typical result of supply chain disruptions, is that if you don't now have enough materials, then you're going to have some underutilized labor. And then and so those are all my basic variables. My non-basic variables are my slack for demand and my slack for wood. Both of those are equal to 0. There's no slack in those constraints. I'm using up all the demand for soldiers that's possible, and I'm using up all of my available wood resources in this current optimal solution. Okay, so sort of summarizing, and maybe then my new objective value is 140. It's less than what it was before I had a crunch on the amount of wood available. So to summarize sort of what happens when you add a constraint is you get a new, new primal constraint. If it's satisfied, then you're done. But if it's not satisfied, then your current solution is not feasible. You need to add it to your tableau as another row in your tableau, and you'll have a negative on the right-hand side. To get rid of that negative on the right-hand side, use the dual simplex method that moves from kind of maintains dual feasibility and moves towards dual optimality. and dual optimality is the same as primal feasibility. And so once you've moved to when you're primal feasible, then you'll be dual optimal, and you'll still be dual feasible, which will be primal optimal. And so it's sort of the story of your initial tableau here, or your initial solution after adding that constraint, is what we'd call super optimal. It's got too good of a objective value, but it's violating one of the constraints. And so you're moving back, reducing the objective value, and moving towards moving towards the feasible region. So that's it for this video on adding a new constraint.